Good evening, students. Today, let us learn the series and parallel combination of cells. So, today's topic is combination of cells. Two varieties of combinations are there. One, series combination, and second one, parallel combination. So to know the series combination and parallel combination, let me explain you. Series combination means, suppose if there are n number of cells, they are connected in series, just like the series combination of your resistance, capacitance. Then here we need to find out the effective EMF of the cell. Means if n number of cells are there, if you replace them and take a very single cell, one cell in place of all the other cells, what will be its value in terms of the all other cells? So to have a very clear picture, we will take only two cells and we can extend it up to n number of cells. So let us consider the series combination first. So before going into series combination, we need to remember these equations. E is equal to V plus I R. What does it mean? It means or V is equal to E minus I R. Here V is your terminal potential difference, E is the EMF of the cell, I is the current flowing through the circuit, R is the internal resistance of the cell that you need to know. V is the terminal potential difference. For the series combination, you see, suppose there are two cells, one cell whose EMF is V1 and whose internal resistance I am taking it here, it will be R1. It is in series with another one. Let's say its EMF is V2 and internal resistance is R2. Try to understand here. Suppose this is the flow of the direction of your current flow. Let's say I is the amount of current flowing through it. Let's say this point is A, this point is C, and this point is B. Now our job is to replace this two cell by a single cell, so that whatever the two cells are doing means they are sending high amount of current to the circuit, and that single cell, after replacing these two, that single cell will also send this high amount of current in the circuit. So the equivalent diagram will be like this. If you take a single cell, let's say the EMF is E, let's say ES, and the internal resistance is like this, and the current sent by this cell is also I. Means this point would be A and this point would be your B. Right? So let us, across VAB, the terminal potential difference is V. If we compare these two diagrams, V, this is nothing but VAB, which is your V. VAB means that we can say which is VAC plus VCB. So which implies V is equal to simply VAC plus VCB. VAC is what? It is nothing but the terminal potential difference across the cell 1, and VCB is the terminal potential difference across the CB2. So which is, we can find by this equation V. So VAC is equal to the EMF of that cell is your E1 and the current sent by the cell is I. So minus I into R1 plus, similarly for VCB, E2 minus I into R2, which implies your V is equal to, which is, just simplify it, let's rearrange, means E1 plus E2 minus I you take common, which is R1 plus R2. And in this case, the value of VAB is the terminal potential difference across this. Suppose here the internal resistance is R. So in that case, for this single cell, this V, the value of V would be, which implies we can write, the value B is, it is simply ES minus I into R. So for V, I have written this, which is equal to this thing, which is E1 plus E2 minus I into R1 plus R2. So if you compare both the sides, you observe ES is equal to simply E1 plus E2, and the internal resistance is nothing but the sum of the two internal resistances. Got it? On comparison both the sides, you find if these two cells, they are connected in series like this, ES is equal to E1 plus E2, your effective EMF is nothing but their addition, E1 plus E2, and R is equal to R1 plus R2. But one thing you need to know here, students, this end is marked to be your positive, this end is marked your negative, and this end is your positive, and this end is your negative. So you see the cascade style, plus minus, they are connected in this way, then only you will get this formula. Else, if any one cell's polarity might be changing, if this way it is changing, means the connection would have been in this way. Suppose either E1 or E2, so let's say you change the U2. For E2, let's say this is negative, this will be positive. So you see here it is plus minus and this minus plus, then your effective EMF would have been, in this case simply write here, it would have been E1 minus E2 instead of E1 plus E2. So keep that in mind. So for n number of cells, you see, if the style of connection is just like plus minus and it is continuous till n number of, then you simply, the net EMF is nothing but the sum of all the EMFs. Suppose at in between any one cell's polarity is reversed, subtract that EMF from the net EMF, then you will get your value. Got it? So this is your series combination. Now students, come to your parallel combination. Again, for the parallel combination, the same formula we are going to use. For the second means your parallel combination. The same formula we are going to use, means V is equal to E minus I into R. So for simplicity, let us take two cells. One cell is here. Another cell is here. Let's say the EMF here it is E1, here it is E2, and let's suppose these two cells, they have internal resistances. I can show it either inside or outside. So let's say, let us put a resistance here, which will give you the value of the internal resistance of the cell. So which is, here it is R1, here it is R2. They are connected parallel. Parallel means one's positive terminal, both the positive terminal they are tapped to 1, and the other negative terminal they are tapped to 1. This R1, R2, they are internal resistance. So that also you keep in mind. R1 and R2 are internal resistances of cell E1 and E2 respectively. See, suppose this cell is sending I1 amount of current and this cell is sending I2 amount of current to the network. So the total current flowing through it, let's say it is I, which is the sum of I1 plus I2. Got it? So if you replace a single cell, whose purpose is to send the same amount of current I1 plus I2, and from this equation we can have our equation like I is equal to how much? E minus, in this case, E minus V by R. From this equation, the current in the circuit means this term will be taken to the left side, V will come here and R gets divided. From this equation you can find I is equal to E minus V by R. Now you see, students, I is equal to I1 plus I2. As these two EMFs, they are parallel, let us mark this point to be A, this point to be V. Means the potential difference, whatever across AB is there, that is called the terminal potential difference across this cell, also across this cell, because they are in parallel. So it is very clear that the terminal potential difference across the cell is nothing, which is VE1. V is equal to E1 minus I1 R1 if you go through this way, because they are connected parallel, their terminal potential difference must have the same value, which I have taken to be V, and which you are getting it from here. For this cell, the terminal potential difference, we can write that formula E1 minus I1 R1, and again this V would be, if you go through this branch, again the same V would be E2 minus I2 R2. So from this equation, I can find I1 is equal to E1 minus V by R1, and from this equation I2 is equal to E2 minus V by R2, or which is simply E1 by R1 minus V by R1, and which is equal to E2 by R2 minus V by R2. Equation 1, equation 2. Now if you replace this two cell by a single cell like this, and suppose the resistance is here, and this is the internal resistance, it is EP, and this single cell is sending I amount of current. This I is equal to how much? I1 plus I2, because this I is what? The sum of the two currents sent by the two cells. So I is equal to I1 by I2. Now that single cell is connected between the terminal A and B. So the terminal potential difference across this cell also, this V. This idea we are getting it. So now if you put the value of I1, I2 in this equation, I will be getting, which implies I is equal to I1 plus I2 means E1 by R1 minus V by R1 plus E2 by R2 plus, this is minus V by R2. Now let us simplify it. Now from this equation I am getting I is equal to simply E1 by R1 plus E2 by R2 minus V whole into 1 by R1 plus 1 by R2. So from this expression, let us find out the value of V. Find out the value of V, which implies V equals to, if you take C, V into, let us keep it in this way, V into 1 by R1 plus 1 by R2 is equal to simply E1 by R1 plus E2 by R2 minus I, which implies V is equal to, formula is, now divide this entire term the right side, so which is E1 by R1 plus E2 by R2 minus I whole divided by 1 by R1 plus 1 by R2. Now what I am doing, I am just separating the term, so to keep this equation in this form, like I can write here, from this equation, so I will be getting V is equal to, simply see, E1 by R1 plus E2 by R2 whole divided by this minus I divided by this. So this term gets divided between this term, you take this to be a single term and I to be another term. So V is equal to, I can write here, which is E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2 minus I divided by 1 by R1 plus 1 by R2. Got? You see this equation is of the form of this, which is V is equal to E minus IR. So if we compare this equation and this equation, I am going to find E is equal to E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. It is your net EMF, or which is simply your EP, means EMF in parallel, and your R is equal to 1 by R1 plus 1 by R2. This is your net internal resistance of the cell. So for n number of cell, this term will extend up to En by Rn divided by, this term will extend up to 1 by Rn. So this is the formula to derive the combination of EMF in parallel and series grouping. So next class we will be solving some questions related to this. Thank you, students.